aerial warfare against a biblical plague. It's an old story, but now scientists like Dr. Julia Kornegay have an answer. She's using nature's own defenses against nature's terror. Joining her in the fight is Dr. Tony Bellotti, who's sending squads of wasps on kamikaze missions against the ravages of nature. Working out of a laboratory in Colombia, these scientists are winning the war against nature's assault. Also in this episode of The New Explorers, forest fire. Terrifying, beautiful, and deadly. And yet today, preservationists are utilizing the rejuvenating qualities that fire brings to forests and prairies. Our new explorer, John Varley, is finding proof that new life thrives beneath the ashes of Yellowstone's forest fires. Hello, I'm Bill Kurtis. It's early morning in South America, and this is a street market in the high mountains of Colombia. There are fruits and vegetables here the rest of the world has never seen. Oh, some are familiar. But our new explorers come here looking for the secrets of the original food, not only to make them bigger, looking for the secrets that can fight disease and drought, hoping to save the staples that we eat, and ultimately, maybe save us as well. The farmers of Pescador, Colombia have been farming these fields all their lives, sowing beans and planting cassava. Year after year, they lost 20% to an insect called the hornworm, and just as much of the bean crop to the bean weevil. It was a hard loss. But they learned to live with it, to harvest what they could to sell at the market, and keep the rest to feed their families.
We've been working on this house since Christmas Day.
And then the scientists came. Dr. Julia Kornegay moved here in 1985 with her family to help. While at Ciat, she was a plant breeder, and like the earliest farmers, she came with dreams of a magic seed that would resist disease and withstand the pests that destroy the crops. But instead of just dreaming about it, she would use science, a patient, systematic approach to find a special seed that would hold the answers to the farmers' problems. Problems like this one. These are some of the most destructive insects in the world, tiny bean weevils attacking the seeds of a bean plant. 300 million people depend on beans for food. This insect can single-handedly destroy a farmer's crop. It happens regularly to the farmers of Pescador.
Here we have the adults, the adult male and female. And the female adults are ovipositing or laying their eggs on the seed. They actually glue them onto the seed, and you'll see them. They are little white specks. After a day, the eggs will hatch, and the larvae will bore down into the seed. So although the actual oviposition or the egg laying causes no damage to the seed, the emerging of the adults is where the major economic losses come from this insect.
Once the adult female lays her eggs on the bean, it takes just 30 days for the offspring to emerge, eating much of the bean in the process. Any beans the farmer has stored are ruined. Working in the South American laboratories of Ciat, Colombia's International Center for Tropical Agriculture, Dr. Cornegay and her team began a search for the special bean that could somehow resist the weevil and fight it off. They knew it wouldn't be an easy journey. There are over 27,000 different beans preserved in CIAT's gene bank, of all stripe and color. Wild beans, domestic beans, beans from Central America, used by the ancient Aztecs and Mayans, and South America by the Incas. If only one of them resisted the insect, it could hold the key to defeating the bean weevil. Their search would take years. While the bean exploration moved forward, the CIAT laboratories were launching a mission against another devastating enemy. This is a healthy field of cassava, a hardy plant that will grow in the harshest conditions, poor soil and foul weather. That's why 800 million people worldwide depend on it. The root is the key. The plant is dug up so the tubers can be chopped and mashed by those preparing the meal. But this is not a healthy plant. Its leaves have been stripped by a creature that flies hundreds of miles to descend on a field out of nowhere and give birth to worms that devour up to 75% of the plant. Dr. Tony Bellotti, an entomologist, has been studying the cassava hornworm for almost 20 years.
Now, down below the plants, they've already defoliated these plants. They've fed on these.
Right.
We see leaves moving,
Right.
a lot of movement down there.
They'll stay like that under this debris for about 2 weeks till they eventually, the adult emerges and then is ready to fly.
If it sounds like the stuff of science fiction, it is the nightmare of cassava farmers and a dreaded enemy of the plant scientist who battles it.
If you have a good attack of these, like we normally find in cassava fields, you would leave this field without any leaves at all on it. It would just completely defoliate the field.
You've got a handful there, don't you?
Yeah.
Now, what do we have?
Well, here you've got several different stages of the hornworm.
This is the smallest. You can hardly see it.
This has just come out of the egg stage now, and it's just beginning to feed on a leaf, as you can see there.
And then over here is the next size.
It's a little, as it feeds, after a few days, it'll get to a larger size, as you see here.
And it just takes a few days to get that.
Yeah, it'll take about 5 days, let's say, to get to that size. Okay,
And
4 or
then
5 days.
It gets bigger and bigger,
Right.
feeding on more leaves,
Yeah,
and we get into this stage.
Right. Now, yeah, this is when it really can do the damage, too, as it gets to this stage. It becomes a feeding machine at this stage. And it will just continually consume foliage until it reaches its maturity and then goes into the prepupal stage.
Which is the head end, the feeding end.
This is the feeding end.
Right there.
Right.
And it just kind of devours the greenery. Then it goes into the prepupa stage, right there.
Exactly.
The very fast movements.
Well,
Why?
they don't like to be disturbed in that stage. It's they're trying to go into a quiescent stage where they want to change into the pupa, and so they don't like to be disturbed at this stage. And if every little, just touch them, and they'll react to it. It's very sensitive in that stage.
And then this is the pupa?
That's the pupal stage, right?
Big.
And they're sort of protected. That's a fairly hard coating on them. And they're fairly protected in this stage. Very difficult to control them in this stage. We do have there are a few insects that you will find in the soil that will actually feed on these, but not very many.
They are sealed in there, but you can see the wings beginning to form.
You can start seeing some formation exactly in that. And as the pupal stage ages a little bit, you can start seeing a little bit more definition of it.
And then the final stage, they will emerge as a moth.
As a moth, right. This is their really mobile stage, and as this stage they can fly hundreds of kilometers, and they can migrate to other cassava fields. We usually find that they will do this in mass.
So there it is, the enemy. One of many that have been here longer than we have. Sometimes they have won. From the Pharaoh's locusts swarming across Egypt to the Irish potato famine of the 1840s, plagues have been a major part of our religious and historical record. For over a century, the boll weevil has ravaged cotton fields in the South. In 1958, the locust wiped out 160,000 tons of grain in Ethiopia, enough to feed 1 million people for a year. There are pests that attack every one of the staples of the world, leaving many farmers in third world countries on a fragile thread of survival. We can battle them with chemicals, but more and more pests are developing resistance to our chemical poisons. So Dr. Bellotti searches for ways to help farmers who can't afford expensive chemical pesticides. He studies how nature does it. An old Arab motto says, "The enemy of my enemy is my friend." And these wasps are perfect examples. The cassava is of no interest to the wasp, but the hornworm is a hearty meal. Preying on hornworm larvae, the wasp will sting its victim, then carry it back to its nest.
He's going to come up ahead. He's going to kill it. He's going to kill it right there.
Even the big worms are no match.
If it's a larger one like this, it will there again sting it again, sort of paralyze it, and then it will start cutting it up or slicing it up into strips, almost like pieces of filet mignon. And it will take these strips, roll it into a ball, and take those strips back to the nest and feed it to the young larvae that are developing in their nests.
Tony's research has shown that a family of wasps can kill up to 100 hornworms in a day, an effective ratio for smaller hornworm outbreaks. It's a prime example of biological control, developing natural, non-chemical methods of saving crops.
Y después, aplicando ese líquido mezclado con agua,
For Dr. Bellotti, the payoff comes from making a difference in farmers' lives. He's also fascinated by the insects.
There's calculations that there might be as many now as 30 million different species of insects. So if you consider the human race as one species, and you look at the diversity that we have in the human race, you can imagine the diversity that's out there, genetic diversity in insects. It's one of the most successful forms of life on Earth. And it is absolutely fascinating to work with them. Right now, I don't know if I can think of working with anything else except entomology. I enjoy it that much.
It's an alien world, strange beings of all shapes and forms, like this cicada shedding its shell. They spark the kind of curiosity that intrigues scientists into lifetimes of study and will continue to lead Dr. Bellotti to yet another means of natural control. While Tony advanced on one front, Julia Cornegay and her colleagues were bogged down in beans. After testing 10,000 types of beans by placing the adult bean weevils on the seeds to see if they would lay eggs, not one bean survived a weevil attack. And then, 5 years after the study began, they decided to test some wild beans. Over 20 years earlier, near Arcelina, Mexico, an American scientist, Dr. H.S. Gentry, collected a primitive bean that he found growing in the hills. They were inedible, odd-shaped, even birds wouldn't eat them. But they were rare, so he saved them. Eventually, the beans from Arcelina ended up at CIAT's gene bank. And when scientists set the weevils on them, the insects starved to death. The seed was resistant. The secret was in its gene. The challenge for Julia and her colleagues was to transfer the gene from the Arcelina bean to beans the pescador farmers were planting. They named it the Arcelin gene after the area in Mexico where it was found by scientists from the University of Wisconsin. Then Julia and her team went into action, crossbreeding the wild bean with other varieties.
Like this. This is hybrid seed now. This has 50% of its genes come from the mother and 50% come from the father. And what we want to do then is to evaluate and select among the progeny those that best express the traits of interest in this particular cross.
Under normal conditions, the bean plant will breed alone or self-pollinate. The pollen from its stamen will fertilize the female stigma. But Dr. Cornegay had to transfer the resistant gene from the arsalan plant to an edible bean plant. She took the pollen from the arsalan plant and gently placed it on the stigma of the new plant. And it worked, producing a hybrid variety of bean plant that was resistant to the bean weevil.
Every day we're evaluating the action of genes and how can we best combine them, manipulate them, take them out or put them in to improve a crop. And then the final product, of course, is a better bean, but it also has to filter down to a practical application which farmers will adopt.
It was a remarkable achievement to create a new variety which can resist pests and disease. But it's also useless if no one wants to eat them. So Dr. Cornegay and other scientists at CIAT let the farmers themselves test the new varieties. In the hills of Pescador, Indians helped the farmers harvest a crop of beans. Today a small threshing machine is broken, so the farmers will have to thresh the bean from the pods in the traditional way. Then they must be dried, spread on a clean surface until the moisture leaves and the seeds can be packed and stored. Some seeds will be sold, and some will be stored for next year's crop. Before CIAT began working here, that was impossible. Farmers were forced to sell all their seeds right away. If they stored them, the bean weevil got to them. That meant each year they would have to obtain new, untested seeds that were often unsuitable to resist the bean weevil and other pests or pathogens. Now, with the stronger arsalan variety, bean yields have increased by 50 to 100%. Dr. Cornegay's team is now testing their advanced beans at CIAT's sister research centers in Central America and Africa, and the new beans are growing strong. Today, as science continues to look at new technology, it's finding answers in the most unexpected places. One example is the Salicornia plant. It's a halophyte, a salt lover that grows in salt water instead of fresh water. It can grow just about anywhere, but its ideal climate is the desert coastline. The seeds of the Salicornia produce an oil that can be used in cooking. Many Middle Eastern countries dependent on imported cooking oil could become self-sufficient, producing their own halophyte and becoming coastal desert farmers within a few years. Another example of plant life adapting to its environment. Perhaps science will come up with a variety of cassava that will adapt to its environment by resisting the hornworm. CIAT scientists don't rule out that possibility. Biotechnologists here are engaged in a long-term project to record the entire genetic makeup of cassava. It's the first step toward identifying the genes that could produce resistance not only to insects but to drought as well, or the ability to yield higher nutritional content. This type of investigation is cutting-edge research, still in the early stages of development. The work that CIAT is doing in Colombia will be shared with other countries all over the world that depend on beans and cassava for their food. It's all part of how scientists are discovering ways to maximize a farmer's natural resources, enabling him to bring his product here. Strolling through this market, the CIAT lab seemed part of a distant world. Here, an Indian medicine man foretells the future by letting a parakeet pick a card.
The parakeet will pick out at random a card telling my fortune. Okay. It's in Spanish, so I'll have to have you... I see. Let's hear what it says.
It says, the person that left you has left a tremendous anguish, but this is going to reduce itself. There is a tendency in you to believe in magical thought and in the intervention...
I came to him, didn't I?
And in the intervention of supernatural forces. Decide yourself to recognize your will, to give more power to your will.
Yes.
There will be little problems during these days, but soon happiness will surround you.
I like
Trust
this man.
yourself and trust those that are around you.
You know, sir, you have a very smart parakeet. Very smart. I'm going to get one.
And what's a medicine man without magic potion?
He says this is water that he brought from the Amazon, and if you take a bath with it, you will pretty soon fall in love.
I'll take it.
Strangely, our scientists may not be as far apart as you might think. Dr. Bellotti has his own magic potion.
This liquid that you see right here is the liquid that comes out of that hornworm. You could actually just decant that off. If you want to get the best, though, is to just put it right in the blender itself.
He's developed a natural pesticide using a baculovirus of the Arenis ello, or virus-infected hornworm. The farmer sprays a liquid virus on his fields. The invading hornworms contract the disease and die before doing too much damage. It's CIAT's version of natural germ warfare.
Back in the early 70s, we found at CIAT in the cassava fields, we found some diseased larvae. We took these into the laboratory, looked at them, realized we had some type of disease that these larvae had, and we sent these off to be identified. Eventually, it was Boyce Thompson Institute that helped us with the identification of the virus disease. So we realized what we needed, if we were going to use biological control, that we needed some type of natural enemy that we could apply or put out in the field whenever the attack occurred. Of all the natural enemies that we had, we realized that the virus disease probably fit this criteria best, in the sense that it was a natural occurring disease of the insect. It gave us very good control. You'll get 99 to 100% control when you use this out in the field. And the chances of something going wrong in the sense that it's going to harm humans or other animals isn't very great. The chance of something going wrong with pesticides, yes. There's a lot of problems with pesticide contamination in human beings in many parts of the world. I think that biological control is a much safer means of controlling these insects.
And that's the point. Using the natural ways, science has achieved breakthroughs. Is there a moment of discovery, a thrill in this business that causes you to say, that's why I got into it?
Yes, there are actually. There are several times when you solve a problem or you understand, for example, inheritance of a trait, or you finally obtain combinations of genes and a genotype that you've been struggling to get for many years, and you finally obtain it. So yes, indeed, that's the nice part. But then between all that, there's a lot of diligent exploratory work that has to be done to get to those points.
The virus-infected hornworm is used as a pesticide in Venezuela and Brazil. It has reduced chemical pesticide use by 60 to 100%. Science has helped these farmers improve their lives in a major way. It just seemed like magic. At first, you